Thank you so much for coming. So I'm Natalia, I'm a lecturer at Bournemouth University, and I'm a researcher. So the thing that I will be talking today, it's not a final product that you can just download to use. So this is an idea that we were working for a while, and I was just want to share that with you. Some tips, some lessons we learned on the go. Hopefully you'll find that useful. Sorry, my microphone is falling. Right. Okay. So the research, who I am first of all. So the research I will be talking about today is conducted in collaboration with my colleagues from Heriot-Watt and Glasgow universities. These are universities I used to work. So there are some colleagues, maybe there are some faces that you recognize, and our students. So we'll start talking about the problem, right? So I'm sure you're all familiar with the case when you're sitting in a lab or in an office, something, and you're surrounded with all those machines, and especially that happens in the evening, right? Or at night when we're just debugging or, fixing our problem. And there are all these computers, and they're just sitting quietly, or they're just, updating Windows or doing something like that. And then just us, sitting on one machine, and our poor PC or poor laptop trying to, do the job that we want. And we wish that we can just use all those resources just sitting there, help us somehow to accelerate, to do our job faster. Well, the problem becomes even more pronounced, severe, when we talk about robots. Imagine that we have a set of rescue robots. So something happened, right? Some kind of a disaster. We take a bunch of robots, we deploy them, they come and they start working. And then they face just the same problem. They're just on their own. Some of them are working, some of them don't. Some of them discovered something and they start, crunching it, data, trying to figure out what's going on. Some of them just walking, because there is just nothing. They just walk back and forward, sitting and waiting for something. So what we want to utilize resources, available resources that are around us. And of course, the solution is load balancing. Yay, load balancing, just sharing everything, exploring resources, just sending our jobs everywhere, and using all the computing power that we have around them. But the first law of distributed systems is don't, right? It means that, you think about distributing something, and the first thing you think, do I really need that? How badly do I need it? Because as soon as we go, the reasons we go distributed, right? The first thing is to accelerate, right? To have more computing power. But then as soon as we start distributing, we find out that our program suddenly is not as fault-tolerant as it used to be, although we go for distribution exactly for fault tolerance. And now it goes much more slower than it used to be, just because of the communication time, because of all those things that are happening. So there are quite a lot of things to consider. When we think about load balancing, when we think about utilizing resources, the first thing that we need to think about, there are these three. Who collects trace information? Who decides what's to, where to move and what we move? So these are the three main things. So for example, who collects state information? Do we have a centralized? Is it distributed, so everybody collects for themselves? Is every program or process that wants to move collects information for themselves? Another thing, who decides to move? Do we have, again, the centralized, prone to failures model, some decision maker? Is it given back to the processes who actually move, or programs that actually move? What we move, processes, programs, what exactly is it going to, flow around? The next thing is aim. And when we work with distributed system, and especially there was a talk by Garrett today earlier about the papers and difficulty of it. And working with the distributed systems, I found that it's very often when we work with them, we start with one thing. And the aim, for example, is reduce execution time. But by the end, when we come to the problem, we aim actually to even the load. We want every process to have the same number of processes. or programs or whatever it is. And then you will see, well, discover that these are actually very different things. And sort of these aims and goals, why we do load balancing in the first place, there must be sort of very shining, like all the time, all through the way that we work with load distribution, load balancing, shining across, saying why exactly we do. Every decision that we make must be sort of illuminated by that. And there are lots of reasons. On load distribution, maybe we want, actually, the number of processes to be the same. Maybe we want reduce the completion time, so the goal must be really, really clear here. And the last thing is complexity of all algorithms. I was always, well, many people are for that, but, sometimes I felt a little bit sort of, I don't know, it was, you look at some problem, right? And my aim was always to make the solution as simple as possible. But then I looked at other papers, and there were these glorious solutions, they're so complex. I thought, am I not doing something correctly? But then there were a number of people, and one of them I really loved. There was a talk by Dropbox when they were talking about scaling. And they were also talking about if you want to work with scalability, if you want to scale things, just make the process simple. Because when you go scale, there are so many things that just, go out of control. They become so much complex. So if on top of that you have a complex decision-making process, that it will be just over crazy. So simplicity is vital. So our solution, not solution, baby, but probably the proposal, the idea that we are working is autonomous mobile programs, and I will describe what it is. So autonomous mobile programs, the first thing is that we move the whole program, right? So we don't move the processes, we don't move parts of the processes, of group of processes, we move just the whole program. So we take it and we move it. The second thing is that on the spectrum, who decides where to move, from decentralized to centralized, AMPs are on a very sort of left spectrum. They're very decentralized, radical decentralization. In that every AMPs, every program that moves actually makes that movement decision itself. And then information is collected, we do information collection on every location. So every AMP is just too much, we figured out, but there is this decentralization, so there is no any centralized point, it's just a blackboard. Load server per location. Another thing to note here is that sort of the only active entity in the whole thing is this program, mobile program. So nothing else sort of makes decision, nothing else decides anything, it's just these AMPs, that's the only thing that decides where to do and how to do things. Aim is selfish. So the aim of every AMP is to reduce its own execution time, and that's it. That's the only aim. And the complexity, so here we go for the simple one. So AMP does some kind of work, some bunch of work, then it stops, and it looks around what's going on, on other machines. And what it does, it just takes information from the blackboard, and it compares whether it's worth to move. Actually, I think I have a implementation, explanation how it works. So it just uses this cost model. So time to complete the work here, in comparison to time to complete on the other machine, plus communication. If on another machine is less, then we move. So we did some initial research with Phil, Peter, and Greg from Harriet-Watt universities. And so initially they were just implemented, right? Like on weak mobility, I think it was Java Go that the implementation was. And what we had a bunch of machines. And then they implemented, and they saw that there are lots of things there. So my job was just to simulate and to understand, try to understand what's going on there. And that's what we saw. So we have different machines. So we have 15 machines. This is a simulation, by the way. And we have 3 types of machine: fast machine, middle machine, so speed, and slow machines. And then this is time. They're not the same one, just, something happens at that period of time. And then we start 25 AMPs, and they start distribution. So this is they start, and this is when they reach the stable state. So they distributed, they occupied the space. But the problem is, are these intermediate movements? So what we realized is that our selfish AMPs, they started doing lots of movements. Because they were greedy, they were selfish. They wouldn't tell anybody that they move. So as soon as they see something, they would just move and so on. And they would keep moving, until they reached a stable state. So we did some tiny, tiny modifications, and we reduced quite a lot of them. And the reduction was just, again, very simple introducing of a representative. So there is AMP that makes decision, and also we introduce this tiny sort of agent representative that goes, checks, says that AMP moves, and sort of we get the reduction of those movements. So how it works? This is an example on two machines. We have two allocations, two machines, machine X and Y, and we have an AMP, and each of those has a load server. Load server is, so the name, it was initially introduced as load server, but it's actually a blackboard, but for consistency purpose, we didn't change it. I think we should at some point, just to make it things clear. So AMP executed some batch of work, and then it stops, and then it requests load server to check what sort of resources available around. It gets information, it calculates whether time completing execution on X location is greater than on Y location plus time to move there. So in this case, yes, and it spawns sort of a tiny representative, tiny agent. Then AMP continues its execution while agent moves to location 1, the second location. When it arrives to that location, it checks, again, what about the load? So what's the situation there? And it checks, and if it's worth moving there, again, it just compares the timing. And if it's worth moving to another location, just notifies the load server that it will move and goes back to the initial location to machine X. When it arrives, AMP just continues execution. So there are just waits when AMP completes execution. When it stops, not completes execution, but completes this chunk of work to do. When it completes, it provides the decision to AMP. AMP informs load server that it's going to move, and AMP moves. On the new location, it just appears the same. So the thing is that we want to come up to a situation when AMP just moves, not doing any work. So before moving and between a sort of making any decision, it should execute some chunk of work. So that's what it does. It executes a chunk of work, then it stops, checks load server whether it's worth moving. This time it's not, and so it continues the execution. So that's the whole algorithm. So what we did, we analyzed properties, balanced properties. There is a paper if you're interested to read on that. We did a relatively large, considered 300 machine simulation. That was a simulation with 3,500 of AMPs. We also did worst case analysis and maximum number of movements here. We also considered all sorts of things. So we considered different networks. We considered different types of AMPs, their numbers, so changing their numbers, how the system would behave. And rebalancing. So there are a number of types of rebalancing, right? So the first one, you would start all AMPs on one machine, and then they would move across the network. The second one, you would add new AMPs, so no new AMPs start. Then you would check if some complete, so removing or die, something happens to those AMPs. So we did all of that. And the interesting finding was that you think that they're so selfish, and they're just, nothing is sort of controlled, and they do everything out just the way they want to do. And of course, the first thing is that that's not going to work. Just too many movements, but actually introducing this simple, representative gave us this thing. And what we found is that the number of redundant movements, actually the maximum one, when something changes, AMP is added, not added, but removed usually, is won't be more than the number of different machines that you have. So for example, if you have a homogeneous set of machines, you won't get anything. When you get introducing homogeneity, different machines, that's when you may get redundant movements. But again, it all depends on from which machine AMP spots the vacant space first, and then there may be or there may not be movements. But for example, if you have q types of different types of machines, then you will have maximum of q minus 1, those redundant movements around. Another thing that was quite interesting to find out is that AMPs actually utilized resources. So while some AMPs were moving around, AMPs that stayed, they utilize resources. So if we look here, this one is on removing AMPs, and we looked at different types. So we removed all from one machine, a certain number from all machines, 4 different scenarios. This is the completion time. And here we have minimum, mean, maximum, and hypothetical. Right, this is hypothetical one. Hypothetical is we removed communication time. So we imagined that communication time is equal to 0. So we started all AMPs on a single machine. Then we distributed them like in 0 time. And this is the time it would take for them to complete. And what we found is that actually minimum that we got in the experiments was less than hypothetical. And the hypothetical is like this, perfect timing. But the thing is that while some AMPs were moving, those that were staying, they were actually utilizing resources, which enabled them to complete much faster. And then others who, arrived later or something like that, they were in the air and they completed later. So all this work was on the right. Sorry. Right, so all that work was on the machines, and now we're moving to robots. And this work was done together with Phil and 2 of our students from Glasgow University. So what we started with, we bought car-kit robots, and the reason for that, they're relatively cheap. So you can get them for 250 each, and just a car kit and Raspberry Pis. So that's what we had. And we used a robot operating system there. So ROS is really famous in robotic world. Who works with ROS, by the way? Yeah, people know ROS, right. So for the rest, just a bit of the introduction. The idea behind ROS, it was introduced in 2007, and the idea behind it is that no single lab or institution can cope with all the technologies coming into the robotics world. So we need to sort of get together and start working on the single thing, and this is ROS. And they provide, state-of-the-art tools, library, conventions, all sorts of things. The attraction of ROS is that you can use as much or as little of ROS as you like, right? So it's just up to you, and it also encourages development, that we all work together. It's pretty big and it's pretty famous. So this is the statistics from July 2018. And around 2,000 active community, more than 10 million lines of code, almost 5,000 research papers acknowledged it, and 130 robots that ROS supports. So it's pretty big, pretty large, and the reason for that, so that's the reason we use it. So quite a big community, state-of-the-art technologies, and that's why we use them in our robots. And this is a bit introduction in how it works. So, for example, we have 2 machines, right? One on robot and one laptop. And there you would have a number of nodes, ROS nodes, so-called. And nodes, they exchange messages to communicate with each other. And then we have a master node. An interesting thing about master node, that for nodes to be, ROS nodes to be able to communicate with each other, they need to be registered with this ROS node, but they communicate directly, so not via ROS node. So it's just quite interesting thing. In the next ROS 2, they plan to remove it, but it's a different story. Anyway, so this is ROS. And this is our implementation, so how we did it. We had 5 robots, and they all had standard mains power, so we just decided to go from there and explain the reason behind it. So when I started working with robots, I thought, oh my God, they're so cool. And we can, just put all sorts of drivers there and do all sorts of things, and we'll do this, cool demo when they will, follow each other. It will be so cool. But reality is, ROS, it's so complex. And working with robots is so complex. So we had this idea of this wonderful demo, and we started it, and then we got results, and we couldn't understand what's going on there. And then we're going backwards, and we're going backwards. So first we removed movements, so they were stationary. There was still something funny. Then we removed the functionality. We couldn't understand what's going on. In the end, we got back, so we removed even robots from there. We had just 2 Raspberry Pis, 2 nodes, master nodes separately, communicating with each other via a wired connection, and just exchanging simple messages like hello world, just to understand what's going on there, because complexity is just enormous. So we had to go back to that state and move on from there to understand what's happening with that robot. So for those of you who are planning to start working with robots, my huge advice is start very simple. Start at the stage where you really understand everything, and then move on from there. Right, so we have here mains power. And this is just robot 1. The same thing is repeated for every robot. So every robot has this action server and load publisher, and then they use this action server, autonomous client, load publisher, load. So it's just repeated for every robot. So what happens is here, for our autonomous mobility, we just use functionality available in ROS. So what we have is that we use publish subscribe, right, to publish load information. And then we don't move programs here. We just move migrate tasks. That's first thing. And the initial sort of program, it stays in the initiating machine. And again, this is because this is a research in progress. So we later plan to change it. But for now, just to check how it works, we use that one. And then communication happens via router, so Wi-Fi communication. And we also have all-to-all connection, so all robots are communicating with each other. We also considered fault tolerance here, because robots so they move. And it's important that, especially when we talk about rescue robots, it's really important that they're fault tolerant. We can't sort of put rescue robots somewhere, and then as soon as they start failing, 10 minutes or 30 minutes into the operation, start sending people to restart those robots or help them to do things. So what we want, we want autonomy. So here we also introduce fault tolerance. At the initial state, we just introduced these 3 things. So we think about originating node and non-originating node. So an originating node is the one that started the task. And we assume that non-originating nodes, they can fail, they can crash, and there are different types of failures that can occur. So we can lose connectivity with those robots, or that robot can just fail. Something can happen to it. And with the originating robot, it can happen that it just loses connectivity. So, for example, it just moved out or something like that, far away from the router. And there are 2 things that we are not considering at the moment. So the first one is that originating node failed. In this case, we don't work with that, because probably if the originating robot failed, then probably it doesn't need the solution anymore, right? So it failed, we don't care about the solution. Everything that robot sent, we just remove, terminate, doesn't matter anymore. And then sensors. So if some parts of the robot fail, we don't track that yet. Right, so what we did, the calculation was routing. right? And we used this route planning, minisync, and G-code. And just to give you an idea how long it takes for a single task on a single core, it will take approximately 50 seconds to execute. Another thing that we did here is that ramp, so we call them ramp, it's sort of reliable AMPs or robot AMPs, whatever you like. They don't relocate, again, because this is just initial research. And so AMPs, as they should be, they must be strong mobility. So they take everything with them, state, data, everything, and they move to a new location and they start everything there. For this one, for this implementation, we just did weak mobility. So it means that when it moves, or state move, or task, whatever moves, it restarts from the very beginning. It doesn't continue execution. Right, and these are a couple of experiments that we did. So we have robots, 5 robots, 1, 2, 3, 4, 5. We started with 5, and we fixed the number of robots, and we fixed the number of problems. And what we started doing, so that's the first distribution, and then we started killing robots one by one. And this one, we call it with time to relocate killing, because we sort of kill one connection of one robot, and then we sort of give time for the remaining tasks to redistribute themselves. So the system sort of to settle, and then we kill the next one, and we keep going. In this one, we don't give the time to relocate. So we kill one, then we kill another one, we kill the next one, so we keep killing. And these are just the distributions here, because there is time to settle. It's this distribution, but we actually present it in that way as well. The thing is that if any of you have an idea how to present data, that will be very much appreciated, because at the moment we don't know how exactly better to sort of talk about it, because it's a distribution. And sometimes you would get 4 AMPs on one machine, and sometimes you would get 3 AMPs on that machine. But it doesn't mean that one distribution is better or worse than another. So we're just presenting in 2 ways, just thinking how better to present that thing. Right, and here we have a mixed failure. So in this case, we would consistently kill, for example, robots, or we would consistently kill network communication. In the mixed experiments, what we did, we did a mixture of killing. So for example, first we would kill network connection, and then we would kill a robot, again, network connection, a robot, sort of mixing how the system would react. And what we found, that the system was reacting almost in the same way. So the distribution was still sensible, and still, we could see that the relocation happens in a sort of, so what we got here, we got an emergent behavior. So although there was no anything controlling that behavior, anything sort of telling what and how AMPs behave, they were behaving due to all those sorts of different failures, they were behaving in a consistent manner, which was a really nice observation. And then we started scaling. So we started with 5 robots, then we went to 12 robots. And here we also have different types of states. So for example, we have optimal distribution, the one that is sort of even, and then we have non-optimal distribution that's a little bit uneven, and then we have at all non-optimal distribution that's not, well, non-optimal is the one that we are considering there are significant skews, right? So for example, we have 15 AMPs, and we would get 5 on one robot and 10 on another. So this sort of skew is not good, but we need to remember that our AMPs, they don't relocate. So this is like the first distribution that happens after something happens. They don't relocate yet. So for us, these optimal and near-optimal distributions, they're quite good. But it's interesting to see that there are definitely, we can observe there is a dependency between number of robots and number of tasks that we have there. So here we probably need to think about the proportion, maybe see the proportion, how many AMPs and how many robots work together the best. Another thing is, what is the group of robots that will be communicating the best? So, for example, if you launch like 50 robots or 100 robots, then even if they're close to each other, probably we don't want to them all to get connected. Probably we want to restrict those connection, or be selective about connections they maintain when they work together. So that was an interesting observation of the outcome as well. Another thing that we did, we fixed the number of AMPs and robots, and we watched what happened with failures. Then we increased the number of robots, and the last experiment is that we fixed the number of robots to 5, and we started increasing the number of AMPs. And so the discrepancy in sort of actual numbers, it changed. So we have minimum 1 here, 35, and maximum 35. Whereas, for example, if we have a small number, the discrepancy, for example, up to 20, it's very, very even. But sort of in related terms, it's going down, which is also interesting observation. I'm not sure what we do about that. So, a bit of summaries and conclusions. Promising results. There seems to be strong bond, strong dependency between the number of AMPs and number of robots, and a number of things to do. So this one, external load, is something we want to explore, but it seems that it's a work of the whole PhD, actually. It's not just, because at the moment I'm a young lecturer, very junior, and I mainly do my project with MSc and final year students. But this one, external load, it's when robots and machines have something else apart from AMPs. And this research should be really interesting, but it seems there's going to be lots and lots of work to consider and read, and how we're going about it and how we measure it and how we sort of reason about it. What is load? Because we can't say, for example, as long as we are below 100% of load, the life is fine. We can reason about, we can understand what's going on. But as soon as we sort of reach 100% load, for example, CPU is 100% loaded, and then we start, we keep adding, the task AMPs and things like that. What's going on there, right? How are we going to distinguish between them? Why, 100% in this case is worse than 100% in another case. So that's really interesting research to consider. Thank you very much. My email, my Twitter, get in touch. I'll be very happy to answer questions. Thank you.
Okay, so we've got a little bit of time for questions. Anyone got any questions?
Yes.
Hi, thanks for the talk. It's very interesting. So at the beginning you were talking about you decide whether you would migrate to another load by looking at the time it would take locally and at the time it would take on the destination plus the transfer time.
Yeah.
Can you still do this if you're not sure to such a high degree how long a task is going to take to complete?
Yeah, that's a tough one. Yeah. So we need to know some kind of a prediction, right? But I suppose, so the examples we're thinking about is sort of like route planning and, some kind of a calculations, where to go, or for example, like image recognition, this kind of problems. So if you think about rescue robots and things like that. So in these scenarios, you sort of can predict, or at least, from experience, just running the tasks maybe a couple of times just to get a rough idea how long they take. So, but yes, you definitely need to know at least, in advance a little bit how long it takes. But if it's indefinite, then yes, that's going to be, it's really difficult to predict. Yeah.
Okay, we got
it's not one.
Front. There you go.
Hi there. So is it the placement algorithm? Does it become sensitive to kind of convoys and thundering herds? Because they do a little bit of work and then they decide whether to move? Do they all become kind of synchronized and all deciding at the same time and then all moving around?
No, it's very much, the idea is very much to actors, right, and humans, because we all sort of have our own speeds, right? And although, you know, it's sort of like for me and for you, right, we have, even if we have the same load, right, but our speeds are different. And even if they are the same, then there are some kind of external factors or something like that, right? Maybe you have two tasks that are the same, I have one task. So they don't get synchronized, actually. No, they all behave in their own. And then the times we talk about, they're also quite tiny. So it's not that, you know, they work for an hour and they stop for 5 minutes or something like that. The times are like seconds, milliseconds. So those time spans are really, really tiny. So when we talk about synchronization, nothing particular happens. Yes?
You mentioned that you were using Wi-Fi for connectivity. How much did the latency and reliability impact the results?
Right, quite significantly. It's not in this one, but in a different one. So we ran a set of experiments, and one of them was just exchanging. And Wi-Fi, I think it's, we haven't measured fault tolerance yet. Reliability haven't been measured. But for sort of time to transfer information, it's like 2-3 times slower by Wi-Fi. Yeah. So, but definitely, I mean, as soon as goes Wi-Fi, I mean, another thing here is that our robots at the moment, they're stationary, right? So we have this grand picture that we'll have rescue robots and they will be there, you know, and things like that. At the moment, we are working with really stationary robots and they're exchanging information to check what's going on there. So here, we also, because they stay on the same time, and even if they're over Wi-Fi, then fault tolerance, they don't particularly happen anything. Right? It's when they start moving around and they start losing connectivity, then when it's going to hit it. But again, you can't move if you have a wire behind you, right? So it's sort of a trade-off. Yes, we'll lose in fault tolerance. Yes, we'll lose in time it takes to communicate. But at the same time, we can be mobile. We can move around now. Yeah. Thank you for the question. It's really a good one. Yeah.
Okay, and I think time for one last final question. Oh, it's close. It's proximity.
Hi, nice talk first. And second question is, have you ever considered, or you already did it, to use some emulator for this, something like a game engine, like, for example, I was thinking to Minecraft, Computer Craft, or this kind of stuff, where you can have emulated the computers and robots.
Right, yes. Well, actually, the thing is that I moved my research from simulation to real world. And the reason for that, with simulation, for your results to be credible, you need to do so much work to make sure that your simulation reflects the real world, right? So what we need to do with the simulation is that we first run the actual one, we sort of get results, we run the simulation, and when we get the results, they're interesting, they're sort of, we can understand things because we can slow down, we can understand what's happening there. But then when we talk and present those results, people start frowning and saying, is it really like actual one? Is it really like real world? So what we need to do, we go to all the simulation and we need to move it back to the real life. So simulation, yes, we used it for AMPs to analyze, but just to analyze what's going on. And with this redundancy, it really helped to understand what's going on. But to sort of, if we talk about how fault tolerant things are and how scalable they are, then at least from my own experience, I don't think simulation is a particularly sort of valid thing to do.
And emulation?
Sorry?
Emulation instead of simulation.
Sorry?
Emulation.
Impression?
It is emulation. It is emulate the stuff you're using.
Well, I don't work with that. So probably if you work with that, we can collaborate on it, but I don't, so don't have experience for that. Yeah.
Thank you.
Thanks.
Great, thanks.
Great, thanks a lot.